Okay, a classic application of Snell's laws is the fiber optic cable. So first of all, I'll give a description, and then on the next slide we have a figure that shows a fiber optic cable. Typically, an optical fiber consists of a cylindrical fiber core that has an index of refraction N subscript F for fiber, and that's surrounded by another cylinder that has a lower index of refraction N subscript C called the cladding. And the purpose of the cladding layer is primarily to optically isolate the fiber if you have a large number of fibers that are packed together in close proximity. Otherwise, you might, if they're touching, have leakage of light from one fiber into another. So the cladding provides some optical isolation. It's not mentioned here, but the cladding can also provide a little bit of mechanical integrity and stability so that should there be slight damage, the damage is to the cladding layer and not to the core. So basically what you want to do is you want to propagate light down the fiber, and we'll refer to the next slide to see a picture of this. But in order to ensure total reflection, you have to have the incident angle in the fiber core equal to or greater than the critical angle. Otherwise, the wave would just leak right out the fiber cable. So let's look at a picture of this. So here's my optical fiber, and here's a fiber that has cladding shown, and then the external material, which is typically air, has an index of refraction of n sub 0, which typically would be 1. So let's look first inside the fiber. In order for the optical wave to propagate down the fiber core, it's got to have successive reflections here at the core clad boundary. And so if you look at the normal to that surface, the critical angle for that total internal reflection to occur would be theta 3. So we would have a relationship or we would have a definition of what is the critical angle theta 3 based on the ratios of NC and NF, the fiber and cladding indices of refraction respectively. So that's going to determine inside the fiber what this angle can be, um, and so it'll have to be that angle or greater. Now notice theta 2 is going to be 90 degrees minus theta 3, so, or sorry, 180 degrees minus theta 3 because we have a triangle here. So it'll be the complement angle of theta 3. But theta 2 is determined by the angle of the incoming light, theta incident. So we actually have two boundaries here. One boundary is the boundary between the fiber and the clad. The other boundary is the boundary between the air or whatever material the fiber is inserted in and the fiber cable itself. So first of all, our incident angle comes in and it's refracted to an angle theta 2. And then based on theta 2 and theta 3 and their relationship, theta 3 has to be the critical angle here for total internal reflection. So that then puts a relationship between the incident angle and what it can be in order for total internal reflection to occur, which is necessary for propagation of the light down the fiber core. And a little bit of applying Snell's law twice, once here at the critical angle, and then the application of Snell's law here and the relationship of theta incident to theta 2 and hence theta 3, we can come up with a relationship that defines something known as the acceptance angle. So the acceptance angle is the maximum value of theta incident for which the condition of total internal reflection remains satisfied. And basically the sine of theta acceptance is 1 over n naught times the square root of the fiber index of refraction minus the cladding index of refraction, each squared. So if you apply this formula, you can calculate what is the maximum value this angle can be for propagation to occur. And then the acceptance cone is the solid angle that's formed by by this cone of acceptance for incoming light. Now, whether or not you even want to have an acceptance cone depends on what your application is. So, if you're trying to transmit information optically, um, then you might want to limit the number of, you might want to actually limit this acceptance cone so that you're not bringing in excessive amounts of light or information. If you're trying to couple energy from point A to point B and just deliver optical energy and you don't really care about a signal, then you might want to maximize this acceptance cone. If you're looking for a specific laser signal um, that is used for the purposes of communication, then you can have some problems. So let's look at the next slide and discuss what those problems can be. So let's assume that we have, a fairly big acceptance cone. So you can visualize that there might be some light, that's incident at a 90-degree, or that's incident perpendicular to the boundary. It just propagates straight down the fiber. And then perhaps there's another angle that the beam comes in where it reflects like this green line. And then at an even steeper angle, this blue line. And so you might, if the blue line satisfies the acceptance cone, you might envision that you have these propagating rays in the fiber that are everything from the blue line to the red line, including the green, and then everything in between. And so this is referred to as the propagation of different modes down the fiber, with the red line, which is going straight down the fiber, being referred to as the axial mode. The green line would be a lower order mode because it's going to have fewer surface reflections. The blue line would be a higher order mode, and then you would have everything in between. So if you look at the lines here, you can see that the red line is significantly shorter than the blue line. And so what does that mean? That means it's going to take longer if you're delivering, for example, if you look at this figure to the left, suppose we have a series of optical pulses where tau 1 is the pulse length and t is the period between the pulses. So you can envision that if we have multiple modes propagating down this fiber, that the ones that follow the blue line actually have a much longer distance to travel because they have these multiple reflections than the red line, which is the shortest distance between the beginning and the end of the fiber. So what that means is, that means that it takes longer if the optical wave is following the blue line path. It takes longer to get from beginning to the end of fiber. So the signal will be slower if it's taking the blue line path as compared to the red line path, which means on the other end, you get these Gaussian looking kind of pulses as opposed to these sharp rectangular modes. And so what that means is that you can see if and this is referred to as dispersion or modal dispersion. If this dispersion gets wide enough, then pretty soon the tail end of one pulse begins to overlap the leading edge of the other pulse, and soon you can't distinguish that there are pulses. So there's a limit to what this period can be, or what the pulse frequency can be, the data rate can be. And you can determine that by basically just comparing, given the path lengths and doing some geometry, you can actually determine these 2 points will touch when the period satisfies certain criteria. So the pulse rate then has a maximum allowable amount, and that's basically the speed of light times the index of refraction of the cladding over 2 times the length of the fiber times the index of refraction of the fiber, index of refraction of the fiber minus index of refraction of the cladding. Now, we're not going to go over the derivation of this equation in this class because that's more left for a class in fiber optics. But you can see how this mode dispersion can become a real problem, and it becomes a fundamental physics limit of really how, in a multimodal fiber, of how rapid the pulse can be, the frequency can be. So here's just an example showing some numbers. This would be a 1 kilometer long optical fiber in air. Fiber core with an index of refraction of 1.52, a cladding with an index of refraction of 1.49. You're asked to determine the acceptance angle, and the maximum usable data rate of signals. So this is just a plug into the formula problem where we find the acceptance angle by applying the formula for the acceptance angle given in the previous slide. We plug in 1 for N naught, the fiber and cladding indices of refraction respectively, and we end up with 0.3, which corresponds to an acceptance angle of 17.5, which would give a total angle of twice that. So now from equation 8.45, which gives the maximum data transmission rate, we can plug in the appropriate numbers again, and you find that basically you get 4.9 megabytes per second. So, so those are some sort of real-world numbers of what transmission optical fibers look like as far as their characteristics.